In this tutorial, we're going to go over organic chemistry, and our focus will be introducing organic chemistry. Introduction just to organic chemistry. So, what is organic chemistry? When you're looking at organic chemistry, it is one of the most important branch in chemistry because it has given birth to many things that are useful in our day-to-day lives. For example, we can talk of production of detergents, production of deodorants such as perfumes, production of lotion. It is all by the utilization of this organic chemistry. Production of drugs in pharmaceutical industries, production of food, production of chemicals, many things. Production of anti-HIV. For example, you can talk of Lanfinava, which is an anti-HIV drug administered by HIV patients. So many things. Production of petrol. Petrol is just isoctane. You discover that organic chemistry has contributed to production of many things. Now, what is this organic chemistry? So we're talking about organic chemistry, just the study of carbon containing compounds. Okay, that is the simplest definition. So we are saying it is a study it is just a study of carbon containing compounds. That is what we call organic chemistry, the study of organic compounds. That is organic chemistry. So when you're dealing with organic compounds, they might not just include carbon. They might include some elements like hydrogen. They might include some elements like oxygen, some elements like nitrogen. They might include elements like sulfur. They might include fluorine. They might include chlorine. They might include other elements like iodine, phosphorus. All these are studied under organic compound. And when you're dealing with compounds which are not hydrogen or which are not hydrocarbon, like when you're dealing with elements or atoms which are not say carbon, which is not rather hydrogen, these elements are called heteroatoms. So heteroatoms are just atoms which any atom rather other than carbon and hydrogen, that is considered to be an heteroatom. So it is very important for you to understand that. Now, before we can look at many things in relation to organic chemistry, let's look at the nomenclature or the way compounds are named. Nomenclature of let me just say nomenclature. When you're dealing with nomenclature, you're just dealing with a systematic way of naming. Okay, so systematic way of naming. Compounds. Okay, that is what we say to be nomenclature. So let's look at prefixes. It is very important that under nomenclature we understand prefixes and suffixes. So when you're dealing with a prefix, it is just a first letter or the first letters of a certain compound. When you're dealing with suffix, the last letters of a certain compound. So we can have a certain compound, for example, let's look at an alkene. How are you able to say this is methane? How are you able to say this is decane? When you look at a certain compound, how are you able to distinguish this? This is what we need to talk about. So when you're dealing with a compound with just one carbon, okay, a compound with just one carbon, a prefix is meth. Okay, I think we'll look at the suffix later on. Let's start with prefixes first. When it has 2 carbon, the prefix we say it is eth. When it has 3 carbon, we say it is prop. When it has, let's say, 4 carbon, we say that is considered to be but. When it has 5 carbon, that is considered to be pent. When it has 6 carbon, it is hex. When it has 7 carbon, that is hept. Okay. When it has 8 carbon, that is oct. When it has 9, that is non. When it has 10, that is, when it has 10 carbons, that is dec. So a compound might have even maybe 12 carbon. We consider it to be dodec. So that is what we need to understand under prefixes. But when you talk of suffixes, they are just the last letters of a certain compound. For example, let's look at few compounds. Let's look at alkane. An alkane, you can see that the suffix there, it is ane. So any compound ending with ane, that is an alkane. Okay, let's talk of alkene. You see that the suffix there is ene. So any compound ending with ene, that is an alkene. We can talk of alkyne. Any compound ending with yne, you consider it to be an alkyne. Let's look at carboxylic acid. Carboxylic acid, also known as alkanoic acid. Alkanoic acid. So any compound you see ending with oic acid, that is a carboxylic acid. Let's look at esters. Esters, for example, ethanoic, ethyl, maybe ethyl methanoate. Okay, methanoate. Ethyl methanoate, like that. That is an ester. So an ester ends with that suffix which is o a t e. We can talk of a ketone. A ketone will always end with o n e. On, that is a ketone. We can talk of an aldehyde. To know that this is an aldehyde, to have a suffix al, we can talk of an alcohol. To know that this is an alcohol, it will have a suffix ol. Which other one can we talk of? Maybe we can talk of an amide. An amide will always have a suffix at the end. It will have amide, for you to know that this is an amide. So you can talk of a lot of things. So that is what you need to know basically. So about suffixes, prefixes. Okay, so that is what you need to know. Then let's look at the organic compounds and how you can represent them. Let's look at representation. Representation of organic compounds. How can you represent organic compounds? So organic compounds are represented by different formulae. Okay, we have what we call molecular formula. What is molecular formula? Molecular formula is just the formula which shows the actual number of atoms in a certain molecule. For example, we can look at a formula for glucose, C6H12O6. This compound is a molecular, this formula rather, it is a molecular formula of glucose. It is showing that there are 6 carbon atoms, there are 12 hydrogen atoms and 6 oxygen atoms. We can talk of ethane. Ethane, the formula is given by ethane C2H6, okay? That is an alkane. So it is showing that there are 2 carbon atoms and 6 hydrogen atoms. That is the molecular formula. When you talk of maybe decane C10 should be H22. Okay, so it's showing that there are 10 carbon atoms and 22 hydrogen atoms. That is a molecular formula. Now let's look at another type of formula which we call empirical. Empirical formula. So when you're talking about empirical formula, you're just talking about now the simplest or the simplified molecular formula. So it's just the simplest whole number ratio of the atoms in a certain compound. Okay, for example, I can have C6H12O6. Once I get to simplify this compound by dividing these atoms by 6, we'll have C H 12 divided by 2, that is 1, that is 12 divided by 6, that is a 2. Then O 6 divided by 6 is just a 1. So I'll get to have C1H2O1, which is the same as saying CH2O. So this formula I've written here, it is the empirical formula. It is the simplest whole number ratio of the atoms in this chemical compound. So that is what we call an empirical formula. We can also represent some organic compound by using a Lewis structure. So what is this about the Lewis structure? Now, when you're dealing with the Lewis structure, this is now a way of representing the valence electrons in a certain compound. You get to represent the lone pairs by using dots and also the formal charge. So let's look at an example. Let's say I have ammonia. So for ammonia, for the Lewis structure of ammonia, you get to represent it like this: NH H. You know that ammonia is NH3, so it has 3 hydrogen. Of course, you represent also the lone pairs. So when you get to represent this structure in this format, we are dealing with the Lewis. You have shown the Lewis structure of this compound. You've shown the lone pairs, the lone pairs you've shown, and also the bonds involved, okay, and the valence. So that is what we call the Lewis structure. Now let's look at another structure. Let's say you want to show the Lewis structure of methane. Methane is actually CH4. So you get to put carbon on the middle, then you show the electrons involved, hydrogens, to be surrounded by hydrogens. So you need to show the electrons bonding. There you show the pair of electron, there pair of electron, pair of electron. So this is the Lewis structure of methane. Okay. There is also a way of representing organic compound by using what is known as Kekule's structure. So it is very important for us to understand Kekule's structure. So you can get to represent using Kekule's structure. So what is it about this Kekule's structure? It is just a structure which shows now the expanded structure of all the bonds present. Okay, this one gets to give or to show the bonds, how the bonds are joined in a certain compound. So for example, you can have, let's say I have ethene. This is an alkene. The formula is C2H4. So when you're representing using Kekule's structure, you get to represent it in this format. So we'll have a double bond there, it's an alkene, then hydrogen like that. So from this representation, we get to see that the bonds, how the bonds are joined in this compound, we've shown. Okay, we've shown the bonds. There's a double bond there are single bonds, and the atoms involved. So we've expanded now this structure. So this is what we call a Lewis structure. I mean a Kekule's structure. We can also represent organic compound by using what is known as condensed structure. Condensed. When you're dealing with condensed structure, let's say I have this compound which is C2H6. This compound is ethane. How can we write the structure? I'll write first the Kekule's structure. So for Kekule's structure, it will be like this. There are two carbon atoms. Then hydrogens like that. So hydrogens, there are 6. If we get to count, you'll find that there are 6 hydrogens, 2 carbons. Then how can you represent using condensed structure? So we're going to start with this. So we have carbon bonded to 3 hydrogens, so we just say CH3. Then we have another carbon bonded to 3 hydrogens, so we say CH3. So this is what we call a condensed form or condensed structure. Let's look at another famous structure which we call skeletal. So this will be number 6. We can get to represent organic compound by using what is known as a skeletal structure. Skeletal structure is also known as a line bonding structure. Okay, a line bond structure. And this structure is the one which is accepted widely. Okay, many countries, according to IUPAC, which is the International Union for Pure and Applied Chemistry, This is the most recognized way of representing organic compound worldwide. So what is it about this Kekule's, this skeletal structure? So for skeletal structure, let's say I want to represent the structure of methane. Methane, you just use a dot because methane contains one carbon. So you use a dot like that to represent that there is a carbon there, and since there is a carbon, meaning that it is surrounded by hydrogen, you don't get to show the hydrogen. We'll look at the rules of representing a compound using skeletal structure. Let's say you have methane. We've talked about. Let's look at ethane. Ethane, it has two carbon. So I'll get to draw using a line. So meaning that there's a carbon there, there's a carbon there, and there are hydrogens, but I won't get to show the carbons and hydrogens. So you just represent using a straight line. Let's say I want to represent the structure of propane. Propane is C3H8. So because there are 3 carbons, I'll say 1 carbon, 2 there, 3. Just like this, I've shown the structure of propane. Let's say I want to show the structure of butane, like that. So like that. So I'll just get to draw 1, 2, 3, 4. So there's a carbon there, 1, 2, 3, 4. And what is surrounding the carbons are the hydrogens. So that is how to represent. Let's have another example. Let's want to represent for maybe heptane. Heptane is C7H, should be 16, because the formula we use is CnH2n plus 2. That is for alkanes. Okay, so for heptane, we're just going to say 1, 2, 3, 4, 5, 6, 7. So 1 carbon there, 2 carbon there, 3, 4, 5, 6, 7. So this is heptane. Now using what we call the bond line structure or the skeletal structure. So let's look at another example. Let's say you have pentane. Pentane, it is C5H12. So just have 1, 2, 3, 4, 5. So this is the structure of pentane using skeletal structure. Let's have another one. Let's say for this time around, let me use an alkene. Let's say I have butene 2-in, like that, meaning that the double bond is at carbon number 2. So I'll say 1, 2, 3, 4. But means 4 because it is C4H8, like that. So the double bond will be carbon 1, 2, 3, 4. As carbon number 2, there will be a double bond. So I'll get to represent like that. So this is butane. Let's have another one. Let's say I want to represent hexene. Hexene is C6H12. So I'll get to draw 1, 2, 3, 4, 5, 6. Hexene. So maybe let's say this is hexene. Let's specify maybe. Let me say it is X3, in, meaning that the double bond is at carbon number 3. So I'll number this one 1, 2, 3, 4, 5, 6 as carbon number 3. So 1, 2 as carbon number 3 there. There's a double bond. So 1, 2, 3 as carbon number 3. we have a double bond there. 1, 2, 3. So we have a double bond, so that is hex 3 in. So this is how you get to represent using skeletal structure. Okay. Now let's look at some formula which you can use when you want to maybe write the formula of a certain compound. Let's start with alkanes. For alkanes, the formula is CnH2n plus 2. So if you want to write, let's say I want to write the propane, the formula for propane. Prop means 3, so I'll say C3H. Where there is N, I put 3, so it will be 3 times 2, that is 6, 6 plus 2, that is 8. So this is the formula for propane. Let's have maybe an alkene. For alkene, the formula is CnH2n. So let's say I want to write the structure for ethene. So for ethene, I will say eth means 2. This prefix, which is eth, means 2. So I'll say Cn, where there is n, I'll put a 2 there. Then H2 multiplied by 2. 2 multiplied by 2, it will give a 4. So C2H4, that is for ethene. Let's have for maybe alkyne. So for alkyne is CnH2n minus 2. Let's have a structure for, let's say I want to write the structure for butane. So it will be C4H, where there is N we put 4, that is 2 times 4, that is 8, 8 minus 2, that is 6, so it will be C4H6. So that is the formula for butane. Let's have let's say you want to write the structure for maybe a carboxylic acid. The formula for carboxylic acid. So for carboxylic acid, the formula is CHN minus 1, H2N minus 1. Then we have the functional group there, which is COOH. So this is the formula. Let's say I want to write the formula for which acid? Let me say butanoic acid. So where there is N, but means 4, so C to be C. Where there is N, I'll substitute 4. So 4 minus 1, that is 3. So C3H. Where there is N, I'll substitute 3 again. 4. That is 4 times 2, that is 8. 8 minus 1, that is 7. So it will be C3H7COOH. So that is for butanoic acid. Let's have a structure. The formula maybe for an ester. When you're dealing with an ester is made up of an alcohol and also a carboxylic acid. So what you get to have is, for alcohol, let me start with an alcohol first. So for an alcohol, the formula is CnH2n H2N plus 1, then OH, the functional group OH. So when you're dealing with an alcohol, you get to find that, for example, I have which alcohol? Methanol, right? Methanol, meth means 1, so I want to write the structure for methanol. So it will be C, meth means 1, so CH 2, 1 times 2, that is 2 plus 3, so it will be 3. Wait, so this is the structure for methanol. Now let's look at for the for esters. For esters, we said an ester is just a compound formed by the condensation reaction between a carboxylic acid and also an alcohol. So for an ester, we'll have the carboxylic acid. The formula is CN minus 1, H2N minus 1. Then we have COOH. We'll combine this with an alcohol, which is CN. The formula for an alcohol is CN H2N plus 1, then OH. But you get to find that this OH will actually react with this functional group, which is COOH. Okay, so this is an acid, so OH will react with the hydrogen there. Because it has reacted with an hydrogen, there will be esterification reaction. So what you get to have as a formula is CN minus 1, H2N minus 1. Then here you will have COO, then continues like CN H2N plus 1. So this is the formula for an ester. So any ester you want to find the formula, you just use this one. Let's have, but you need to know that for an ester, the carboxyl chain, or should I say the acid, the number of carbon atoms in an acid might not always be equal to that of an alcohol. Okay, so you need to put into consideration that. So let me put one with a prime there to show that the number of carbon atoms might not always be the same. Okay, so these are the formula you need to know when dealing with or writing maybe the structure of certain common organic compound. So you need to know these formulae. And in this session, we are gonna end here.